All right, welcome everyone. Thank you for joining us today. Welcome to Diagnosing Heating and Cooling Problems in Homes with our instructor, Russ King from Coded Energy. My name is Danica with 3C Ren from the County of San Luis Obispo. And before I pass things off to Russ, I have a few logistical slides to go over. Next slide, please. A few quick Zoom reminders before we get started. Please make sure you are on mute for the duration of the training. We highly encourage questions, and if any questions come up, feel free to put them in the chat or raise your hand and we can unmute you. This session is being recorded, which will be shared with you along with the slides in the next few days. And this course is eligible for both AIA and ICC units, which will be distributed based on attendance. Next slide, please. Just a few quick words about who we are. We are the Tri-County Regional Energy Network, also known as 3C Ren. We are a collaborative partnership between San Luis Obispo, Santa Barbara, and Ventura counties. 3C Ren is funded by ratepayer dollars collected through the public goods charge found in our utility bills. The benefit of being ratepayer funded is that there's no cost to those we serve. And as a regional energy network, we're able to return these funds into our local economy, which has historically missed out on these funds. Next slide, please. 3C Ren currently offers 6 programs focused around 3 services: incentives, training, and technical assistance. Our training today is part of the Building Performance Training Program, and you can find additional trainings and learn more about our other services by visiting 3c-ren.org. And with that, I'll hand it over to Russ to start today's training.
Thanks, Danica. Hello, everyone. Welcome. Hopefully there's not too much background noise. It's kind of an interesting situation. I'm actually broadcasting from a camp trailer parked in the parking lot of the South Point Casino and Hotel in Las Vegas. We had some scheduling coordination issues, but I'm here for a conference, the HVAC Trainers and Educators Conference. It's one of the best conferences of the year. And I decided I would take some time out of my conference schedule and teach this class for you guys. Unfortunately, the cell signal in my room was actually worse than the cell signal in the parking lot. So I'm down here. My wife and I are driving around a little camp trailer. So it's very cozy here. I just hope you're not getting a whole lot of background noise because I am parked relatively close to a road. But anyways, this is one of my favorite topics, diagnosing heating and cooling comfort problems in homes. Just a little bit about myself. If I hit the right button, there we go. My name is Russ King. I'm a licensed mechanical engineer in 3 states. I'm the CEO of a company called Coded Energy Inc. We're the developers of Quick Model 3D. It's a new HVAC design software. We also have a version that will write a CBEC res file, so you can open it in CBEC res and run it. I've been doing this for a while. My first job out of college in 1988 was doing energy code compliance, and I went on to do HVAC design and all that good stuff. And I'm very pleased to be able to share my experience with you guys, and hopefully it helps you out. There's my email address if you have any questions about anything we talked about today, russ@coded.energy. And then if this kind of stuff interests you, I have a blog, and I post to it, maybe every couple months or so. I'm not as regular as I should be, but there's a lot of interesting topics there related to HVAC, kind of with a homeowner focus, but also, a very broad target audience that I, aim my blog articles at, my rants sometimes. But some of the slides that you're going to see in this presentation actually come straight from that blog. And so if you need to get a little bit more information about that, and then occasionally I'll refer to my blog too. If there's a topic we simply don't have time to talk about, I'll say, go see my article about friction rate or whatever it is. Okay, so it's a pleasure to be here to bring this information to you. I appreciate you taking time out of your day to sit through this. We are scheduled to go for an hour and a half, and it probably won't take quite that long unless I do my usual thing and go down a rabbit hole somewhere and really kind of get off topic, which I tend to do, but I will try to stay focused. All right. So today's topic is comfort problems. The reason this is so kind of near and dear to my heart is because I ran two mechanical engineering departments where we specialized in residential HVAC design for production homes. And so all of our clients were the big production home builders, the Taylor Woodrows, the KB Homes, all the big production home builders we did work for. And I was very fortunate that the company we worked for, or that I worked for at the time, we had HERS raters. We had field people that would go out and test houses after we did the design, and they would send that information back to us. And so I got really good feedback on that. But the other interesting thing was a lot of these big production home builders, they have divisions all over the country, and so we'd be working for a certain division, like the Las Vegas division, or the Central California division, or the LA division, or whatever. And they would say, "Hey, Russ, I was talking to my associate in one of the other divisions, and they're having a lot of problems with homeowner complaints in one of the subdivisions. And we were wondering if you could help us out since you do our design for our division." And so I ended up doing a lot of that. I would very frequently get asked to go look at houses by the same builder that we did not design. And I would go in and try to figure out what was wrong with them, why they weren't working correctly. And the first thing I always did was I told the builder, send me the plans and we will run some load calcs on those plans and we will do a rough duct layout on the house. And then I would take that information and I would go look at the actual house. And when you're armed with that information, it's really easy to find out what's wrong. 90% of the time it was things like an upstairs downstairs issue. And you could look at the plans and say, okay, well, my design says there should be two 12-inch ducts going to the first floor, and you guys have one 8-inch duct and one 10-inch duct. So clearly there's an airflow problem. And sure enough, that would be the issue. So the whole point of this, and I'm gonna give you the spoiler alert right now, is one of the best tools for diagnosing heating and cooling problems is the design process, how you design a system to begin with. Okay, because most of the problems that you're going to run into are design problems. Okay, and so let's just kind of go through the different types of complaints that you might hear from a homeowner. Okay, so the main one are temperature issues. You could have humidity issues, or a house is just too humid. We don't have that too much in our climate. We're considered a hot, dry climate. Even you folks on the Central Coast. I live up towards Sacramento. I've done a lot of about 30% of the design work I've done is in Las Vegas, including they don't have humidity issues. But guess what? One of the very few houses that I did design where they had humidity issues was in Las Vegas, of all places, and they actually have a negative latent load. It's drier outside than it is inside the house. But due to occupant behavior and how the occupant was running their house by taking showers and not using their kitchen exhaust fans when they're boiling water, and their bathroom exhaust fans and all that stuff, they actually created a humidity problem inside their house in Las Vegas, which was very surprising to me. Another one you might get is high energy bills. Most homeowners don't know what to expect on their energy bills. And so it'll be kind of rare that a homeowner will call you up and say, "Hey, I'm a little concerned about my energy bills. They seem to be too high," because they don't really have a basis of comparison. Unless they live in a subdivision and their neighbor lives in the exact same floor plan, they can talk to their neighbor and say, "Hey, what are your monthly bills?" And their neighbor says, "Oh, they're about 150." And they go, "Oh my goodness, mine are 350 a month." So clearly there's an issue. So you do occasionally will get high energy bills, or people just will say, "This just seems high to me," and then there's not a whole lot of basis to go by. But anyways, that's another one. I occasionally get complaints about noise. A homeowner will say, "Yeah, when my AC kicks on, it is just loud. I can't even watch TV, it's so loud." And then you have to diagnose, what kind of noise is it, where is it coming from, is it coming from the registers, is it coming from the equipment, and all that other stuff. And then another complaint you might get would be dust. I've actually had homeowners say, "We live in this brand new home and it really should not be this dusty. We are continuously dusting off all of our furniture. Seems like there's dust everywhere and we don't know where it's coming from and what's causing it." Another sort of related one to that is you might, I get complaints of if you look at your ceiling registers on your ceiling, you might get these black, looks like almost like smoke stains coming off of the registers. That's actually dust typically, but it looks like smoke damage or something coming out of the registers, and that's a similar issue actually. And just so you know, one of the most common causes of that are things like oil candles. You know, the oil candles with the floating wick in them. I went to a lady's house one time who was complaining about this black soot on all her supply registers, and I walked in her house and she has 10 oil candles burning. I said, well, there's your problem. I don't even need to come inside your house. I can tell what your problem is. And I took a piece of white paper and I held it about a foot above one of these candles for about 5 seconds. And then I showed her the piece of paper and there was a big black circle in the middle of the paper. So those really give off a lot of soot. Regular candles even give off quite a bit of soot too. So anyways, this is just kind of a smorgasbord of the type of complaints. And the interesting thing is, well, we're only going to focus on temperature issues today, HVAC, heating and cooling problems. But what's interesting is a lot of these other problems stem from some of the same issues. So if you can solve your temperature issues, it's very possible that you can also solve some of these other issues. Okay. So we're going to focus on temperature issues, temperature complaints by the homeowner. So some of these complaints fall into different categories. This one I already mentioned is probably the most common one. Is in two-story homes, your upstairs and downstairs temperatures are very different. Okay, you have it's usually hot upstairs, cold downstairs, and that can be either in the winter or the summer. All right, and this vertical separation of temperature we refer to as stratification. Okay, as we all know, cooler air is more dense and so it tends to settle, and warmer air is less dense and it tends to rise, and we call that stratification. But sometimes it may not be it. I've actually had it be the opposite, where in the summertime the air conditioner is running and the upstairs is more cold than the downstairs. That's the opposite of thermal stratification, and that's usually caused by bad duct design. Okay, and we'll talk more about that. But anyways, the vertical separation of temperature we tend to refer to as stratification. All right, and then another very common problem is different temperatures between rooms, even on the same floor. You could have, as you see in this diagram, you've got these three rooms over here are warmer than these other three rooms on this side. Okay, and so figuring out what that problem is always interesting. And then for some bizarre reason, it's always the baby's room is the one that has the problems. It's the homeowners, I don't know if they're just trying to, get your sympathy or whatever, but that'll always get the warranty people hopping at the builder's office when the homeowner calls up and says, my baby's room is always freezing. But anyways, another place is family rooms. Family rooms tend to have just real control issues, and it's typically going to be in the afternoon, and it's typically going to be more of a problem during the air conditioning mode, and the family room just gets hot in the afternoon. And one of the most likely causes of that is what part of the house is most likely to have a sliding glass door? And that's going to be the family room or the kitchen or the dining room. And those sliding glass doors let in a lot of light. And because it's a door that people like to go in and out of, they tend not to close their drapes quite as much or their blinds or whatever. And then you get that pointing west and you get that low afternoon sunshine. And guess what? That family room is going to roast. So it's basically a little solar oven that's happening in the afternoon. So that's another very common type of temperature issue that is related to uneven temperatures from room to room. Okay. And then you can also have stratification within a single room. You can have it be cold at the floor and have it hot up at the ceiling. And I tend to get this gets noticed a lot in bedrooms that have bunk beds, because the poor kid sleeping on the bottom is freezing and the poor kid sleeping on the top is roasting at night, and it's it's the same night. That's an indication of stratification. It's a vertical separation of temperatures, and that is most likely caused by thermal stratification. Is that warm air will rise, and And what typically causes that sort of thing is poor mixing of the air. So something like a ceiling fan running backwards would do a really good job of mixing that up and preventing that from happening. And then sometimes rooms that have high vaulted ceilings will tend to, because you have a more of a vertical distance for the air to separate, it just separates more. Okay, so vaulted ceilings tend to be rooms where this is a problem, and then any place where you have a loft of some sort also can be called open to below, where you have like you go up the stairs and there's a railing at the top of the stairs and you can look down on the first floor, and so you have basically you have a two-story open space with people standing at the second floor level. Okay, that also is a big opportunity for warm air to rise, and you typically get sort of a stratification issue happening there. Okay. Then another temperature issue is that the system just simply doesn't keep up. Okay. You set your thermostat for a certain temperature, and let's say you set it for 75 degrees in the summer, and on a really hot day, it never gets to 75 degrees. It just runs and runs and runs and runs and runs, and it can't satisfy the thermostat. Okay. And then same sort of thing in the wintertime. You set your thermostat to 70 degrees, and on the really cold days, it just never warms up to 70 degrees for your thermostat to shut off. Okay. So that is, we call that the system is not maintaining the set temperature of the thermostat, or not reaching the set temperature of the thermostat. That is typically blamed on undersized equipment, that the equipment is too small for the house. Okay. And of course, and if you call an HVAC contractor and they come out there and they look at it and they go, oh yeah, you're not reaching temperature. Clearly your equipment is too small. And so, you've heard the expression where when you're a hammer, everything looks like a nail. Well, when you're an HVAC contractor, every problem looks like an HVAC solution. And so their suggestion is going to be to put in a bigger piece of equipment. Well, guess what? That may not be the solution. That may not be the best solution. A better solution might be to look at the house. What is wrong with the house? Maybe there's something wrong with the house. The equipment is fine. It's just the load of the house is higher than they expected it to be when they size the equipment. Okay. And so we'll talk more about that. Another common complaint is drafts, and that's basically when you just have moving air that's moving across your body and it just makes you uncomfortable. Um, Even air that's what we might consider warm air will feel cold if it blows across your body and the temperature of the air is lower than your body temperature. All right. So if our body temperature is around 96 degrees, anything less than that blowing across our body is going to feel cool. And on a hot day, that's good. But on a cold day, we don't like that. Okay. And that's going to be one of the big complaints about heat pumps. You probably, heat pumps are the big thing now with electrification and decarbonization and all that good stuff. But one of the problems with heat pumps is that they don't blow as warm of air as, say, a gas furnace. Okay. A gas furnace might blow 120, 130 degree air, whereas a heat pump might only blow 90, 95, 98, 100 degree air. Okay, if you're lucky. But if it's blowing right on you and it is mixed with the room air and is less than your temperature, body temperature, it's going to feel cold. And so one of the first complaints people get after they install a heat pump is that my heat pump's blowing cold air. And that's not true. It just feels cold to you. But if it's warmer than what you've set your thermostat set point to, it will warm your house. So if you set your thermostat set point to 70, you can theoretically heat a house to 70 degrees with 71 degree air, as long as it's warmer than the set point. Now, blowing 71 degree air is going to feel very cold, but you can do it theoretically. But a heat pump will actually blow air that's more like 90 degrees or something like that. It's just that if you happen to be standing directly under a register, it's going to feel cold. Okay. But these drafts can also come from doors and windows and leaks and all different kinds of stuff like that. Also, in my house, for example, we have floor registers. Okay. And on milder days, when our air conditioner runs, it blows really, really cold air. And that's partially because the ducts are a little bit undersized, and I just haven't had a chance to get around and fix those. But it blows really cold air. under my desk. It blows cold air directly under my desk and it makes my knees ache. And I'm like, oh, this is terrible. I don't like this. And so as a mechanical engineer, what do I do? Well, of course, I take a shoebox and I cut three sides off of it and I set a shoebox over the register so that it blows it away for me, because that's what us mechanical engineers do instead of actually fixing the problem. But the point is that the system could be doing exactly what it's supposed to do. It just doesn't feel right. Okay. All right. So when you go in and you're talking to a homeowner has complained about their heating and cooling system. All right. And it's very important that you know how to ask certain questions, because if you just go in and if you just let the homeowner rant and vent about their heating and cooling system, they're going to tell you all kinds of stuff. And some of it may be very misleading. Okay. So it's very important to have a set of interview questions prepared. And what that does is it kind of stops them from ranting and raving about it. It just say, okay, sit down. I'm going to ask you some questions. Please answer these questions as best as you can. But the other thing is it makes sure that you get certain things answered that you need. Okay. And one of the first things you need to do is identify the symptoms. Okay. A homeowner is going to have their theories about what's wrong with their system. Oh, our air conditioner is way too small. Well, you don't want those kinds of complaints. You want to know what the symptoms are. All right. What is the symptom that they think the cause is the undersized equipment? So you're going to ask them some questions. And what you're trying to get to is the symptoms so that you can diagnose the symptoms, not the homeowner. Okay. So you need to use very precise terms. So don't ask them like, do you feel hot? Okay. Excuse me. Because some people, when they are in a humid environment, they will say, I feel hot. But what they really mean is they feel muggy. They feel like, the air is thick around them. It makes them sweaty. And so you need to ask them some very specific questions like, do you feel warm? Do you feel cold? Do you feel muggy? Do you feel sticky, sweaty? Do you have a dry nose? Do you have a dry throat? Those sorts of things. That's a more direct way to get to what they're trying to express to you. Okay. Then ask them, when does the problem go away? Clearly this problem doesn't last 24/7, right? At some point, the problem seems to resolve itself. What makes that problem go away? Is it that the sun goes down? Is it that they have to close the drapes? Do they put on a sweater? Do they close off the vents? What resolves the issue? Okay, because that can be a really good clue as to what the problem is. And then it's always good to ask them, in terms of thermal comfort, what's your favorite part of the house? Where do you go if you really need to get comfortable? Okay. And then those rooms are going to become your baseline. Those would be the rooms that establish what that homeowner considers to be comfortable. Okay. And then you can compare the uncomfortable rooms to those rooms, the comfortable rooms. Okay. So the other thing is to identify, obviously, I mean, this is kind of obvious, but you need to formalize this question process. Okay. So identify when the problems occur. Do these problems occur during the heating season or the cooling season? Do these problems occur when the system is not running, or do they occur when the system is running? Do these problems occur on mild days? Okay, there are certain thermal comfort problems that are actually worse on mild days than they are on extreme days. So it's always worth asking that question. Clearly, most of the problems, excuse me, are going to occur on the extreme days. Okay, but you will have situations where mild days have more common things like upstairs, downstairs stratification can actually be worse on mild days. And then you kind of always want to question, without being too accusatory, is ask them how they operate their thermostat. Ask them, do you leave your windows open? Do you leave your doors open? How do you operate your thermostat? And I'm sure you've all heard this before, but it's worth pointing out to a lot of homeowners is that the best way to operate a thermostat is to set it at a temperature and just forget it. Just leave it there. Don't touch it. Okay, but many homeowners, especially in your guys' climate where you have, really mild parts of the year, um, homeowners will like to, you say, turn off their air conditioner during the day. And then when they get home at the end of the day, they're like, oh, my house is hot. I'm going to turn on my air conditioner. And they expect it to cool down right away. All right. Well, that's just not how systems are designed to work. All right. If you designed a system to reduce temperature in a house, it would be much bigger than to design a system to maintain a comfortable temperature in a house. All right. And so I use the analogy of if you're going to operate your house, you should operate it more like your refrigerator. How often do you change the temperature of your refrigerator? And it's almost never. They set it to whatever it is, and they just leave it at that temperature. And then don't operate your house like you would your car. All right. Everyone wants to get into their car and turn on their air conditioning full blast and have it cool down or heat up, as quickly as possible. That's just simply not how houses are supposed to work. Okay. And it's always worth explaining that to a homeowner. I had a builder client who did a very poor job of explaining. In fact, they told their homeowners that their air conditioner would work more like a car air conditioner, that they could turn it off during the day. And this project was in Fresno of all places, and so the homeowners had this expectation that they could operate their house like a car air conditioner when it simply wasn't designed to do that. And then we had a whole bunch of problems with homeowner expectation issues in that particular subdivision. So we had to educate the builder to educate their customers how to properly operate their thermostats. Okay. And then, of course, identify where in the house do these problems occur that they're complaining. Is it the upstairs? Is it the downstairs? Is it the master bedroom? Is it the baby's room? Things like that. Okay. So, and then the other thing is and really this should be done before you even get there, unless you happen to be an HVAC tech, and you're going into a house and you know how to diagnose equipment problems like refrigerant charge or blown capacitors and all this other stuff. But for this particular class, we're assuming that the equipment itself is working, that it is putting out cold air in the summer and is putting out warm air in the winter. The fan is running, and that they've resolved any mechanical issues first before we start getting into this part of diagnosing homeowner complaints. Because clearly, if the air conditioner is broken, you got to fix that first. Okay. And then let's say the tech has been out and they've done everything they can, the equipment is working like it's supposed to, but the homeowner is still not satisfied. Okay. Now we step in and we say, okay, what is going on with this house? What is causing these issues? So once faulty equipment has been ruled out, there's really only three basic things that can cause the vast majority of comfort problems. Okay. One of them is poor occupant behavior. They're just not operating their system the way they're supposed to. They're operating like a car, like I mentioned, or they're leaving doors and windows open, or they're leaving fans running all the time, or they just don't understand that that their house needs to be operated a certain way in order for it to be, optimal in its comfort and its efficiency. The next one is that the load of the house is higher than it should be. Okay. Now we're lucky in California, at least for new construction. We have very strict energy codes, and every single energy feature in a house needs to be documented on paper, submitted to the building department before they build the house. All right. So we have good records of what the house is supposed to be in terms of energy efficiency and building features and R values and the types of windows and stuff like that. Okay. And when we do a design on a new construction house, that's what we use. We use that information, we plug that into our load calculations. Well, occasionally things go wrong. The house isn't built the way they say they were going to build the house. This actually happened a lot in Las Vegas because they don't have as strict of energy codes and building inspection and stuff like that, at least back in the day when I was doing a lot of design in Las Vegas. And if you guys recall, oh gosh, when probably late 90s, early 2000s, low-E windows first started becoming really popular in production homes. And the California Energy Code changed and really required, it didn't require low E windows, but it certainly encouraged low E windows, and you basically needed low E windows to pass the code. Um, the manufacturers couldn't quite keep up with manufacturing as the low E windows as fast as they needed them for all these subdivisions that were being built. And so the manufacturer would say, well, let's just throw a few clear windows on the truck. They'll never know the difference. And so these clear windows got installed in these homes that where the rest of the house was low E. And and a low E window, just to give you an idea, there's a number called the SHGC, the solar heat gain coefficient on a window. A clear dual pane window will have a solar heat gain coefficient of about 0.8. Okay. And what that means is 80% of the heat, 80% of the light that is heat that strikes the outside of that window, 80% passes through. Okay. Um, a low E window can have a solar heat gain coefficient down around 0.3 or lower. So that means only 30% of the heat will pass through. So that's essentially a window that's less than half the size of a clear window. All right. And so it makes a big difference. It makes a huge difference on your load calculations. And we had a lot of situations where we would go out to these houses in Las Vegas and they would be having a room where it just wouldn't be comfortable. And we would look at the size of the ducts, we'd measure the airflow, and everything looked good. We said, okay, well, the system is performing like it should. And then we start looking around, and we had this little device. It kind of looks like a stud finder. And you'd put it on the window, and you'd press a button, and it would tell you if that window was a low E window or not. And guess what? It was I wouldn't say it's not common, but it wasn't uncommon to find a lot of clear windows, just random clear windows installed in a house where the rest of the windows in the house were low E. So things like that. Another problem we would run into is these one-story houses where there's two front bedrooms that kind of stick out from the front of the house towards the street, and you've got the main roof slope would come down and sort of cut those off. Well, in order to access the attics above those two bedrooms, they had to cut a hole in the roof sheathing of the main roof slope. They sometimes refer to that as California framing, and they had to cut a hole so that they get out there and insulate those front two bedrooms. Well, we'd go out to this house. We had our little thermal camera. We'd poke around. We'd see these rooms, and we'd look up, and the ceiling of these bedrooms are red hot. And we're like, oh wow, let's go up in the attic and look. And we can't even get to the attic above these bedrooms. They didn't even put access so that someone could get in and insulate these. So clearly they weren't insulated. So things like that. So the building is not built how it should be. Okay. Another big one that's kind of hard to diagnose is if they build a house much leakier than they're supposed to. So in California, we don't require a blower door test. We only require a blower door test on new construction if they're claiming a really tight house and they want to take extra credit for building a tight house. So if the building department and the general contractor don't do a good job making sure that the house gets sealed up real well, the house will be much leakier than we assume it to be. But we would never know unless we actually did a blower door test. Okay, so we'll talk about some diagnostic tests we can do later on. And then last but not least, one of the biggest causes of comfort complaints is that the HVAC system simply was not designed properly. Okay, either they didn't do a good load calculation, or they didn't size the equipment according to the load calculation, or they didn't design the ducts correctly. All right. Of these three issues, occupant behavior, defects in construction, or the system not being designed well, number three is by far the most common cause of comfort problems. Okay. I can say from my personal experience that of all the houses I've gone out to look at where the homeowner was complaining, and these were mostly new construction homes that only been around for a year or two. The two biggest causes of these comfort complaints were oversized equipment and undersized ducts. All right. Those were the two biggest problems. Now you might say, well, oversized equipment, how can oversized equipment cause issues? I will show you. I will demonstrate to you exactly why oversized equipment will actually cause more comfort complaints than undersized equipment. Okay. Everyone's afraid of undersizing equipment. Oh, I'm going to round it up a ton just to be safe. Well, guess what? That extra ton of cooling may actually cause the homeowner to not be happy in their house as opposed to being a little bit undersized. Okay. Now, if you way undersized a piece of equipment, which almost never happens, you'll certainly get comfort complaints. But guess what? Those comfort complaints will only happen on the really extreme days. All right. If you oversize equipment on the milder days, it's even more oversized. And so it's going to exacerbate whatever problems the oversized equipment is going to cause. All right. We're going to go into that in a lot of detail. All right. But the point is that the vast majority of comfort complaints are caused because the HVAC system was not designed correctly. Okay. Now, the good news is that that's fairly easy to diagnose. All you have to do is take the house, do a really quick, what I call after the fact design. So you're basically kind of redesigning the system how it should be off to the side and trying not to pay attention to how the house actually is designed. You do a load calc, you do equipment selection, and you figure out how much air needs to go to each room. And then you figure out what size duct should be serving each room. Okay. And then you go and you compare it to the actual house. And that doesn't take very long. With all the technology we have today, you can do that in an hour or two. Okay. And so you've got this design, and this design is how the house should be behaving. And then you compare that to how the house actually is designed. And the first thing you look at is equipment size. Okay. And that's what I was saying. I would do a load calc on a house, and I'd say, okay, this house should be fine with the 3.5 ton system. I go out to the house that's having a problem, and it's got a 5 ton system in it. And I go, aha, that's a problem. An oversized air conditioner is going to cause issues. Okay. And then the other thing I would look at is duct sizing and airflow. Now, when you oversize equipment, you need to also oversize the ducts, but they never do. They only oversize the equipment. They leave the ducts at typical size ducts, the good old rule of thumb duct sizing. And now you've got equipment that's too big for the duct system. That's going to cause even more problems. And then last but not least is how the ducts are laid out. Okay. Um, where are the registers located in the room? Where are the returns located in the room? Things like that. Okay. Of these three bullet points that you see right here, equipment size, duct sizing and airflow, duct layout and register locations, equipment size is by far the worst. Okay. It will cause the most problems. However, if you oversize your equipment, but then do a good duct design on that oversized equipment, you may not notice it as much. Okay. But as soon as you couple that oversized equipment with undersized ducts, you're almost guaranteed problems. Okay. And then after that, duct layout, register locations, return grill sizes, stuff like that, those are much less important. And when I teach HVAC design classes, one of the things I like to say is that if you have properly sized equipment and properly sized ducts with good airflow, it almost doesn't matter where you put the registers in a room. It almost doesn't. I like to say good airflow, good equipment sizing forgives a lot of sins. Okay. So after that, you don't have to be quite so precise where the register is, what kind of register it is, and those sorts of things, as long as your equipment is not oversized and you got good duct sizing with good airflow. Okay. All right. So how do you evaluate an existing system for equipment sizing and duct sizing? Well, simply doing a proper design on a house, it's an important investment in time. But unfortunately, the way the HVAC industry works with the low bid and all this other stuff, they've gotten away from doing load calculations. They've actually been disincentivized to do a good design on a house because it's not a level playing field. They know that their competition's not doing it. They're trying to bid against these other people who aren't taking the time to do it. And it's just really pushed the industry down. It's caused a lot of issues. All right. But you can actually do a really quick and dirty design on a house in just less than an hour. Okay. Using the same basic design principles. You just kind of do a quick and dirty estimate. And I get asked this all the time. I get someone will come up to me and say, "Hey, I've got this in my house," and they'll sketch it out on a napkin or whatever. Does this look good to you? And I can actually say, yeah, that actually looks okay, or it doesn't. And there's a trick to it. It's not that difficult. All right. So let me show you really quick how you can do this. So let's assume, for the sake of argument, that good, quote unquote, good airflow is 400 CFM per ton. Okay. So if you have a 3-ton system on your house, 3 tons of air conditioning, good airflow is going to be about 1200 CFM. Okay. Now, some people argue that no, that's more like a B minus. You should actually have more like 450 or whatever. But let's just, for the sake of argument, just say 400 is okay. Um, just so you know, a new system in California, the lowest you can have by code is 350 CFM per ton. Okay. 400 CFM per ton is not much more than 350. All right. Think of 350 as a D minus. All right. Because 349 is an F. You don't pass at 349. 350 is a D minus. 400, honestly, it's probably like a C minus, somewhere in that area, but it's okay. All right. But we're going to use that as our target for our evaluation. In humid climates, which we are not a humid climate is like Florida, Louisiana, Mississippi, South Carolina, all those really muggy states. In a humid climate, you actually want less airflow. So in humid climates, they actually design to 350, where in California, 350 is the lowest you're allowed to go by code. Okay. So we're going to use 400. So let's say somebody sends you a really simple sketch of the duct system in their house, or you climb up in the attic and you sketch it yourself. Okay. And it doesn't have to be perfect. It just needs to kind of show the duct sizes and how they split and where things are. It needs to know the return duct size. That's very important. And then we're going to have, so let's say this is a horizontal furnace up in the attic of a house. Okay. The end where all the supply ducts come off of, we're going to call that the supply plenum. All right. And then the end that the return duct comes off, we're going to call that the return plenum, or just the return side of the furnace or air handler. All right. And then the ducts that are attached to the supply plenum, we're going to call those supply trunks. And a trunk is a duct that splits. Okay. A duct that goes straight to a register, we're going to call that a branch. So you got trunks and branches. Okay. Now, one of the interesting things is there's a few places in this layout where we know that the airflow should all add up to the total system airflow. The total system airflow is that target that we're shooting for of 400 CFM per ton. Okay. In this layout, there are 3 places where it should add up to 400 CFM per ton. The first place is the return. Okay. In this example, there's only one return. So if we have 400 CFM per ton, it should all be going through that return. Okay. The other place is all the trunks that come off the supply plenum. In this example, we have 4 10-inch trunks. And if we're shooting for 400 CFM per ton, we know that much air is going to have to be passing through these 4 trunks, because that's the only way for the air to leave the plenum. All right. And then the last place is at each supply register. So if we were to add up all of the airflow coming out of all the supply registers, those should add up to our total system fan flow. Now, there are places where we're not quite sure, like this intermediate trunk here. We can't really use that for much of an evaluation, but we can still use those 3 places: the return, all the supply trunks, and then all the supply branches, all added up. Okay. So that's what this says here. There are 3 important sets of ducts that affect overall airflow: the main supply trunk at the plenum, the supply branches serving all the registers, and then the return ducts. Okay. All right. And then here they are pointed out. So those are the main supply trunks. Those are all the supply branches. That's all the ducts that are touching a register, a supply register. And then the return ducts. Okay. In this example, there's only one. It's very common to only have one. You might have 2. In some houses, they actually put a return in every bedroom. which has its own set of issues, but you would do a similar analysis on that. Okay. And then this little table here, you're welcome to use this table, but basically all I did is I took a ductulator, a duct calculator, and I said, okay, at a fairly common friction rate, how much air should I get out of a 4-inch duct? And the particular ductulator that I was using said at a friction rate of 0.1, you should get about 20 CFM. A 5-inch duct should give you about 50 CFM. A 6-inch duct should give you about 80, and so on. And I just filled out this little table, assuming a friction rate. Okay. Now, a friction rate is a very complicated number, but just suffice it to say that a very simple duct layout like this example here will have a friction rate of about 0.1. The more complicated the duct layout is, the lower the friction rate is going to be. That's counterintuitive. You would think that the friction rate would go up, the friction rate actually goes down. Okay. So it's a commonly used friction rate for examples. When you do a design, you actually calculate a friction rate. When you do a design, when you're designing a system, you will actually calculate a friction rate. But what I've seen, after doing thousands and thousands of designs, that a simple system like this one will have a friction rate of around 0.1. So that's a reasonable number to use as a target. Okay. If you want to learn more about friction rates and how they work, go to my blog. It's russellking.me and if you search for the word maybe, it'll come up. But I have an article wrote friction rate explained maybe, because it's a very complicated topic, and it takes you have to read it a couple times before it sinks in. Okay, so here's what you do. You take this little table and you go to those 3 places where you know that the air should all add up to the total system fan flow. And one of those places was the 3 10-inch ducts. So you look at the 3 10-inch ducts and you say, what should they be giving me? So here a 10-inch duct says about 300 CFM. So 300, 300, 300. So those should add up to 1200 CFM. By the way, and I apologize if I missed this somewhere back at the beginning. Maybe I didn't miss it, but this house is a 3-ton system. Okay, a 3-ton system. And so it should be moving 3 times 400. So it should be moving about 1200 CFM. Okay, so then we look at the 3 10-inch trunks, 300, 300. Hey, that's dead on. That's perfect. Okay, so we got perfect airflow coming out of our trunks. All right. Now we do the same for the supply branches. So we look at all the supply branches, we just add them up. There's an 8-inch, a 4-inch, an 8-inch, an 8-inch, et cetera, et cetera, et cetera. And wait a second. Oh no, I'm sorry. This is a 3.5-ton system. My mistake. This is a 3.5-ton system. Sorry, I should put that in an earlier slide. Yeah, it's right there. I'm sorry. There it is right in front of me. So handwritten on the diagram is 3.5-ton system. So 3.5 times 400 is 1400. Okay. So 1400 CFM is our target. All right. Based on this 3.5 tons. So we go to our 10s and we add those up and it's only 1200. So that's not good. That's not good for a 3.5-ton system. For a 3-ton system, it would be fine. But we want 1400 CFM. We've only got enough trunks to handle 1200. So that's a problem right off the bat. Okay. Then we go to all the supplies and we add up all the supplies. So an 8-inch duct should give us about 170. A 4-inch duct should give us about 20, et cetera, et cetera. We add those all up. And then even our supply branches aren't giving us 1400. They're only giving us 1270. Okay. So that's a problem. Then we go look at our return. It's a 16-inch return on a 3.5-ton system, which I see all the time. I look at 16-inch and I go, oh my goodness, a 16-inch is only rated for 1050 CFM. We need a system that can move 1400 CFM. So we actually have 3 bottlenecks in the system, the worst being the return. The return can only handle 1050 CFM, but we need it to handle 1400 if this was a good system. Okay, so that's an easy fix. So what would we need? We would need at least an 18-inch duct to handle 1400 CFM, but that's cutting it close. Why not go to a 20-inch duct? There's nothing wrong with going bigger especially on the return side. So if we were to replace this 16-inch duct, I would say, heck, let's just go to a 20. Since we're doing it, let's just go to a 20. 18 inches cutting it kind of close. Nothing wrong with the return. That's a little, there's nothing wrong. There's no such thing as an oversized return duct. Okay. Um, but we also have problems at the trunks. Okay. Um, the trunks, these 10-inch trunks here, we actually really needed 312 or 412-inch trunks. So replacing those trunks, that's a bit more work, but it's not out of the question. Replacing all the supply branches, that's a lot of work. All right. At that point, you're basically replacing the entire duct system. But the point is we've evaluated basic using really basic design strategies and using an assumed CFM per ton and an assumed average friction rate. We've shown that this is not a good duct system for a 3.5-ton system. Okay. Now that's at 400 CFM. The minimum allowed in California is 350. So 3.5 times 350 is 1225. Let's see, our supply branches are okay for 350. Our trunks were a little under at 1200, but our return is still way undersized. Even for 350 CFM per ton, our return is way undersized. Okay. So that's how you do it. If you want more information, go to my blog article. All these diagrams and stuff are from there. Okay. So this is just an illustration of how you can use the design methodology to evaluate an existing duct system very quickly and easily. It'd take me 15 minutes to do this. Okay. So here it is all laid out for you. And so we can say, all right, this is a bad system. We're undersized on the main trunks, we're undersized on all the branches, and we're way undersized on our return. So clearly this isn't good. There's our trunks, there's our branches, and there's our return. Okay. Now, if we did 350 CFM per ton, which is the lowest you're allowed to go by code, we're still off on some of the stuff. Okay. The other thing that this doesn't even address, we're only looking at total system airflow. What this evaluation doesn't even address is this the right duct for this room? Is an 8-inch correct for this room? Is an 8-inch correct for that room? Is an 8-inch correct for that room? That's what we refer to as air balance. All right. The first goal of a duct system is to handle all the air that it needs to handle. That's the 400 CFM per ton. That's the first goal. The second goal is then to make sure the air goes to the rooms that it needs to go to. All right. But to do that evaluation takes a little bit more work. Now we would have to do a room by room load calculation. All right. We'd have to look at each room and say, what is the load of this room? What is the load of this room? We could add that all up and we could evaluate the size of the system. And then we could evaluate the individual rooms and how much airflow those need. Okay. So that's a little bit more work, but it's not that difficult. There's some amazing software programs out there. There's some amazing technology out there. If you guys haven't played around with it yet, and I can't remember if it's in my slides or not, but there is an app. I will drop it into the chat. It is called QB Casa. CUBI.CASA. That's their website, QB.CASA. It's a phone app. All right. You put it on your phone. Do this to your house. You'll be amazed. All right. Do this to your house tonight. Put it on your phone. Go into one room. Point it at the baseboards. Press record, and then just walk through your house and point your camera at all the baseboards throughout your entire house until you get back to where you started. All right. You'll send that file. You'll send that off to QB Casa. And then the next day, you'll get a floor plan of your house that looks like an architect drew it. It's got doors, it's got windows, it's got the rooms labeled. It is phenomenal. It is stunning how accurate it is. I tested it out on my 83-year-old mom. She scanned her house and it came out perfectly. So it's really amazing. So do that. And the reason that's important is because to do a good load calculation, you really need a good set of plans. All right. Because you need to calculate, especially if you're going to do room by room load calculations, you need to know the walls, the floors, the ceilings, the windows of each individual room. And to do that, you need a good set of plans. Okay. Now, once you have those plans, you can load them into a load calculation software. Like ours is called Quick Model. There's other ones out there. RightSoft is a big one. Elite is a big one. Those are the three that also do duct design. But there's also some really cool programs out there. One is called Conduit. It's a lidar based load calculation software. You put it on an iPad and you scan the house, and it does a load calc right then and there. Okay, it's instantaneous. It's very cool, but it doesn't do duct sizing and stuff like that. Okay, but anyways, so it's very easy to go out to a house and do a room by room load calc on an existing house. Okay, um, then the design process, which is our evaluation tool that we're talking about today. But if you want to get into actual HVAC design, it's the same thing. These are the manuals. These are the industry standard for designing residential HVAC systems. Okay. Let's see. We've got manual J is load calculations. Manual S is equipment selection, and manual D is duct design. Those are the big three. Okay. There's only three approved software programs out there that do all three of those, J, S, and D. All right. And I'll show you what those are in just a second. But it's worth knowing that there are lots of other manuals too. So there's manual RS, which is a overview of residential design, the whole process. Okay. Manual RS just kind of folds it all together and tells you about the overall design process. Manual T. Manual T is for terminal selection. That helps you size register locations. Okay. Manual H is specific to heat pumps. All right. Manual S is equipment selection. So you do your load calcs, and then you have to pick a piece of equipment that's appropriate to those load calcs. That's what Manual S is all about. And Manual S will cover heat pumps, very, very detailed. By the way, there is a new Manual S out, just came out very recently, and it covers heat pumps much more in depth. All right. But Manual H goes into a lot more detail about different kinds of heat pumps. So Manual H is going to talk about geothermal heat pumps, ground source heat pumps, air to water heat pumps, and stuff like that. Manual H is going to cover all that. And then this last one is very interesting. It's called Manual LLH, and that stands for low load homes. So you've all heard of passive home and all the super tight homes and stuff like that. Houses are getting so efficient that when you do the load calculation for them, the equipment is so small for this house, for this giant house. You get this big house with teeny tiny equipment on it. That poses certain problems. Okay. The biggest one is just getting good mixing from your supplier. Okay. How do you get that? You're only blowing. So we're talking like 1,500 square feet per ton. So you got a 3,000 square foot house with a 2-ton air conditioner in it. That 2-ton air conditioner is only blowing 800 CFM. By the time you divide it up to all the rooms, you're only blowing 40 or 50 CFM into each room, or less sometimes. Okay. How do you take that tiny bit of airflow and get good mixing in that room? And that's a challenge. It is a big challenge. And so for these really low load homes, one of the ways to address that is to only blow air into part of the house at a time. So that you're blowing 800 CFM into half the house and getting good mixing, and then blowing it into the other half. So you have dampers that motorized dampers that open and close. Anyways, that's what LLH is all about. It's very interesting, and it's becoming more and more important as we're building more and more energy efficient homes. ACCA is Air Conditioning Contractors of America, by the way, if I didn't mention that. They have some really good standards and checklists as well. You may have heard of their QI checklist. That is a requirement for many rebate programs and incentive programs for HVAC. They will say you must follow the ACA QI standard and things like that. That is a free download. If you just Google ACA QI standard, you'll get it. It's a PDF file. They have another really good one for maintaining a system, the QM standard, quality maintenance standard. All right. And then they have a whole bunch of other stuff. All right. So really good information there. A lot of this is free. Their manuals are definitely not free. Their manuals are quite expensive, actually. But they're really, really good information. And honestly, they're mandatory if you're going to do HVAC design. All right, you really should have copies of these. And they're all available at ACA.org. All right. Okay. So load calculations are critical to properly sizing heating and cooling equipment. All right. For air conditioners, undersizing an air conditioner will cause a house not to cool on very hot days. Okay. It will not cool on very hot days, which is a minority of the time. It's not the most common situation. And by the way, I see Steve Mann asked a question. Thank you, Steve, for asking this question. Any recommendations for software? Of course, but of course, I'm biased as well. Our software is called Quick Model, KWIK. We I used RightSoft pretty much my entire career. There's another program out there called Elite. So RightSoft, Elite, and our software Quick Model. Those are the only three programs out there that that do manual J, manual S, and manual D. There's a lot of them out there that just does load calculations, okay, and really good ones. It depends on if you're doing existing homes or new construction, but they'll all give you about the same answer. Okay, if they're approved by ACCA to do manual J load calculations, they should all give you about the same answer. The question is, how easy was it to get that information into the software? All right. If all you need is a really simple block load, something like Conduit, or there's another one called Amply, they're LiDAR based, and you just scan the house and it'll give you a load count. There's a couple online ones. I'm drawing a blank now. CoolCalc. CoolCalc is an online one. Not super accurate, honestly. It can be accurate if you take the time to actually measure the house, but unfortunately, they have a sort of a shortcut built into their software, and they just look at a Google Earth. They look at a Google Earth map. They look at the age of the house and they estimate glass area. Not a super accurate way to do it, but it is very, very quick. But if you're going to go on and do duct sizing and equipment selection, the Quick Model, our software, RightSoft, and Elite are the only three that are certified for that. So good question. Okay. If you if you undersize an air conditioner, it's only going to not work on very hot days. If you oversize an air conditioner, it's going to cause problems all of the time, and those problems are going to be worse on the mild days. Okay. Real quick, there's another question. When manufacturers are making equipment that are 300 CFM per ton, how does that fit in with minimum airflow for California at 350 CFM per ton? It doesn't meet the requirement. Unless there is an exception to that. It's the high velocity, small duct high velocity. So Unico and SpacePack are exceptions to the 350 CFM per rule. And I think that target is 300, if I recall. It might be even less than that. But they are allowed to have lower CFM. You might also be thinking, Trevor, of the 350 CFM per ton, which is a minimum for existing systems in order to do an airflow test. Okay. That is a target for existing system, but if it's a newly installed system, it has to pass at 350 unless it's one of the small duct high velocity systems that I just mentioned. So maybe that's what you were talking about. All right. Let's see. So what happens when you oversize an air conditioner? You do a load calc on your house. Let's say the load calc says a 2-ton system is fine, but you play it safe and you put in a 3-ton system. Okay, so now you got your actual load said 2 tons, you install a 3, so you're 50% oversized. Okay, just by going at 1 ton. So what does that do? Well, when the thermostat calls for cooling, you've got this great big air conditioner that's going to blow really cold air into this house. And it's going to blow a lot of it. Okay. And what's going to happen is it's going to satisfy the thermostat very quickly. The house is gaining heat at a certain rate, and you're going to remove all that heat by blowing cold air into the house really, really quickly. Okay. And that's going to cause the thermostat to satisfy very quickly. And so what happens is we call that short cycling. It runs for a very short period of time and it shuts off. then it waits a little while, it runs for a very short period of time, it shuts off, and the cycles are very short. Well, imagine a room that's far away from the thermostat. Okay. The thermostat turns the air conditioner on. You're blowing really cold air into the house and you're blowing really cold air into that room that's far away. But then the thermostat gets satisfied. What's going to happen to that really cold air that you've just blown into that room? It's going to sink. You've blown very cold air into a warm room, and that air is going to stratify. It's going to sink to the ground, and you're not going to get good mixing. Whereas if you installed a 2-ton system that your load said was appropriate, it's going to have much longer run cycles. In fact, on really hot days, it's going to run for a long time, hours. Your system could run for hours. That's not a problem. Okay, that is not a problem. When the system runs for very long periods of time, you're blowing air into the house that's not as cold, and you're not blowing as much of it. So it takes longer for your thermostat to get satisfied. And so your house mixes and mixes and mixes and mixes. And all this air passes through your house multiple and multiple times. And eventually your thermostat will shut off. Okay. And then you have very, very even temperature throughout the house. Right. You don't get that when you have short cycling. The other problem with short cycling, I mentioned it causes excess stratification. It causes uneven temperature distribution. And guess what? That larger piece of equipment costs more to run. Even though it's running less time, it costs more to run because it's a bigger piece of equipment. And here's the other thing. It takes a while for an air conditioner to reach its rated efficiency. So let's say you install a 16 SEER air conditioner. Now it's SEER 2, all right, a 16 SEER 2 air conditioner, but it may take 20 minutes before it hits 16 SEER. It has to run for 20 minutes before it hits that 16 SEER. Well, what's going to happen if your system shuts off every 10 minutes? It's never going to get to that 16 SEER. So that's another problem with short cycling is the air conditioner doesn't run long enough to reach those stable conditions so that it can run efficiently that it's rated to. All right. So, and then last but not least, short cycling. How long would your car last if all you ever did was stomp on the gas pedal or stomp on the brakes? That was your two options. Stomp on the gas pedal, stomp on the brakes. Stomp on the gas pedal, stomp on the brakes. How long would your car last if that's the way you drove your car? It's not going to last very long. All right. And the same thing is true of your air conditioner. And when it short cycles, it's running full blast and then it's shutting off. It's running full blast and it's shutting off. That is very bad for the equipment. It's bad for the compressor. It's bad for the motors. It's bad for the fan motors. And it's just not good. Your equipment's going to die much sooner. Okay. So many issues caused by undersizing equipment. The negative impacts of oversized equipment can be mitigated. All right. There are some things you can do. If you oversize equipment, there are some things you can do to lessen the impacts of that. One of them is to have multi-stage or variable capacity equipment, which is great, but it's also more expensive. Okay. Variable speed equipment is much more expensive than single speed, but it's becoming quite common now, especially with the heat pumps. Most of the heat pumps you get today are variable capacity. And so what that does is allows them to run at it allows them to act like smaller pieces of equipment so that you don't have those oversizing issues. But here's the thing. Too many contractors will install oversized variable speed equipment thinking that's going to solve the problem. And a good friend of mine has a great quote. He said an oversized variable speed an oversized variable speed equipment is the world's most expensive single speed equipment because you've paid for all this for all this variable speed capacity, but it's only going to run on the lowest speed. Okay. So it's not a good idea. So if you do install variable speed equipment, you should size it as though it's single speed equipment. All right. And then what happens is on those milder days, it can throttle down for the part load conditions. You do not size variable speed equipment so that it can throttle up. All right. You design it so that it can throttle down to variable speed to the part load conditions. All right. Another thing that can help a lot with oversized equipment is and undersized equipment for that matter too, is have good duct design. Good airflow will squeeze more capacity out of undersized equipment, making it behave like bigger equipment. All right. And then for oversized equipment, if you have really good airflow, what happens then is you get better mixing in the house. You get better distribution, you get better mixing and things like that. Okay. So good duct design, good system airflow can help resolve some of the issues caused by oversized and undersized equipment. Okay. So historically, the most common method of equipment sizing in California, and as I'm learning the rest of the country, the most common method of equipment sizing was rule of thumb and trial and error. All right. So you've probably all heard the 500 square feet per ton, or maybe on the coast it's 400 square feet per ton, or sorry, 600 square feet per ton is bigger. But they use these square feet per tons. All right. That is not a load calculation. That is a rule of thumb. It does not consider leakiness of the house. It does not consider orientation of the glass. It does not consider R values of the walls or anything like that. It's looking purely at square foot of the house, but it was how most equipment was sized in California. And it's too big. It's safe. They're playing it safe. They're playing it big. All right. And so they would build these houses and they'd go, and then they would undersize the ducts for the size of the equipment, and the homeowners would complain. And they go, well, gosh, maybe next time we should add half a ton. Let's make it bigger. And so they've actually evolved. The equipment's gotten bigger, ducts have gotten smaller, and homeowners have gotten less happy. Okay. Well, to look at the silver lining on this, if you're working with existing homes, there's a very, very, very good chance that the equipment is oversized in the house that you're looking at. I would say the average house in California, the equipment is oversized by as much as 50%, at least 30%, maybe as much as 50%. Okay. What that means is that you have an opportunity there to downsize the equipment. All right. And if you downsize the equipment, it's more likely to be appropriately sized to the ducts, so you don't have to make the ducts bigger. There's probably still going to be some undersized ducts. Okay. But there's opportunity there. And then if you couple that with some weatherization, some sealing, some added insulation, stuff like that, the homeowner's going to end up much happier. They're going to have a more comfortable house. They're going to have much lower energy bills. Okay. And they're just going to be happier. So all of this oversized equipment that's out there today in all these houses, think of that as an opportunity. All right. Think of that as an opportunity to improve those houses. That is low-hanging fruit that we can improve the homeowners' energy bills, their comfort level, and all this other stuff. Okay. So the importance of good design as far as duct sizing goes, and let me do a time check here at 4:13. We're getting close. Okay. I probably should speed up a little bit. So duct sizing, clearly good airflow, is good overall airflow is the most important thing first. Okay. And then after that is getting good airflow to each register, making sure that the air has good balance. And what that is you have to do a room by room load calculation. Okay. And we're going to go to the next slide. Do a room by room load calculation. And that tells you exactly how much air each room needs when you do a load calculation. And it's very simple math. If a room is 10% of the total load, it needs 10% of the airflow. It's that simple. All right. So when you do a load calculation, a room by room load calculation, and then you say, I want to move a certain CFM per ton, right there, you've got your answer. How much air does that room need? It's a very simple math. And then that will allow you to size the duct to that room. Okay. That's all built into the software. Overall undersizing of ducts, especially return ducts, will reduce total system fan flow, which will reduce capacity and efficiency of the equipment. So when you start choking off the entire system, and remember our example where the return duct was way undersized, by that one simple mistake of undersizing the return duct, they've reduced the airflow in the entire system. And what that does is it reduces the capacity, the ability of that system to heat and cool, and it reduces its efficiency. So it makes it cost more to do that little less cooling that you paid for. All right. So it's kind of a double whammy. When you undersize ducts and reduce overall system airflow, it hurts in two ways. Your capacity and your efficiency suffer. Undersizing one or two ducts might cause poor air balance. So that's where you're going to get uncomfortable rooms compared to the rest of the house. Okay, uneven temperatures. And then if you do that and you undersize the returns, you're going to have uncomfortable rooms and overall problems. All right. So it just gets worse and worse and worse. So remember, equipment cannot be properly sized unless you do a load calc. All right. And think of the load of the house as the demand, it's what the house needs. Okay. And then you size the equipment to appropriately heat and cool that house. And think of what the equipment gives you, which we call the capacity. Think of that as the supply. So it's a balance between supply and demand. You can have too much capacity, you can have not enough capacity. All right. So it's getting that right in the middle, that sweet spot. And manual J is what shows you how to calculate your load, and manual S shows you how to pick a piece of equipment that's appropriate to that load. They have oversizing rules and they have undersizing rules in manual S. Okay. So that's what that's all about. Individual ducts cannot be properly sized unless you know how much air needs to go to each room. And the only way to know that is to do a room by room load calculation. Okay. There's two kinds of load calculations. One's called a block load. That's the entire house is one number. And the other is called a room by room load. And a room by room load is necessary to design a good duct system. To obtain the load calcs, you'll need to take a manual J class, and you'll know how to use ACCA certified load calculation software. There are several programs out there. Okay, and here's the slide I was thinking about. So this is RightSoft. This is what I used almost my entire career is RightSoft right here. I taught a lot of classes on Elite. I taught classes on both RightSoft and Elite. And then when I had the opportunity to write my own software, that's what I did. I hijacked my son's career. My son is a computer science degree from UC Santa Cruz. He wanted to design video games. And I said, you know what? I have a better idea. Let's design a really nice HVAC software program. And so this is Quick Model. But these are the only three programs that do manual J, manual S, and manual D. If all you need is a load calculation, there's probably 8 other programs out there that will just do a load calculation. Okay. And there's some pretty cool ones that I mentioned. Conduit and Amply are the LiDAR based ones. So whichever software you choose to use, learn the software. You're going to have to take a class on that software. You can't just say one day, I want to learn how to do HVAC design. I'm going to buy some software, because you're really doing two things. You're learning the design process, which is manual J, S, and D, but then you're also learning software. Okay. And you can do both of those at the same time. You just have to be patient. But you definitely want to learn software. Now let's talk about testing a house. Okay, there are some tests you can do to a house. You can measure airflow. That's a passive flow hood, powered flow hoods, velometers. There's even a plastic bag and stopwatch method. It's not really impressive to watch, but guess what? It's actually kind of accurate. And if you want to learn more about that, Google this right here, LBNL 47382. They did a big comparison between all these different methods for measuring supply air, residential supply air. And one of the things they tested was the plastic bag and stopwatch method, and it was actually kind of accurate. It's funny. But anyways, when you do air balance, the important thing is for airflow to be close to each other, relative to each other. Okay, think of it as more as percentages. All right, and I'll explain that a little bit more here. When we compare target airflows to measured airflows, the total airflow is never going to be the same. It'll be off a little bit. And if you compare parts of a total to parts of a different total, they're going to look funny. So what you should do is compare percentages. All right. So you'll say if this room needs 150 CFM, what's the percent of total of that number? Okay. And you compare that percent to what you measure. And you measure a room, you say, okay, what's the percent of that measured airflow to the measured total? And you get a percent. Compare those percentages. Don't compare the measured numbers, okay? Because that's going to be misleading. And here's an example. This is not a very good example, but this is a real case. This was a house where I did a design on the house. The installing contractor, without telling the builder, basically threw my design away and did their own. And then the homeowner started complaining. And I went, okay, well, let's see what's going on. And I went out there. My first comment was, well, you didn't follow our design. And then I started doing an airflow balance. I had a register in the stairwell to deliver 257 CFM. They didn't even install that register. So right off the bat, I know there's some issues going on. But then look at this game room. I had a target of 187, or sorry, 186 was what I wanted that room to have. And when I measured it, it was 195. So you say, oh, okay, well that's good. You measured more than what the target was. All right. Um, but you have to look at percentages too. And there are cases where you might have more airflow, but it has a lower percentage, and that's not good. And like I said, this is not the best example, but look right here. The total of measured was 988. My design called for 1200, and the total was 988. So what good does it do to compare these individual numbers when the totals are off by so much? So what you do is you compare the percentages. Excuse me. All right. You look at the percentages and you say, okay, is this percentage close? And if it's close, then the balance should be okay. But clearly this house had a different problem. That was that it just wasn't delivering enough air. So the first problem was to fix that 988. Okay. And then for two-story houses, you can compare upstairs and downstairs. That's always a useful thing to do. Is what was the total upstairs? What was the measured upstairs? What was the design upstairs? What was the design downstairs and total downstairs? And then do that too. And what you'll typically see is that most houses actually need a majority of the air to go downstairs because there's more square footage, there's more glass on the first floor. Okay. But when you go out there and measure, what you're going to find is most of the air is going upstairs. And that's usually because they didn't do a good duct design. And air is going to take the path of least resistance, and it's all going to go upstairs because there's usually a furnace in the attic. Okay. If not, that changes, obviously. But it's a very common situation. Then you get hot upstairs and cold downstairs. Very easy to diagnose. Okay. Blower door tests are great for measuring infiltration. Infiltration can have a huge impact on your load. And if you don't do a blower door test, you basically have to guess what it is. And sometimes you can guess really wrong. So doing a blower door test is always worthwhile. Measuring static pressure across the air handler. Okay, that's a good number. If you find the equipment specs for this air handler, whether it's a furnace or a fan coil unit, it will tell you that at a certain total external static pressure, it should move a certain amount of airflow. So if you have the specs for this piece of equipment and you measure that static pressure, that'll tell you the airflow. Okay, and then you can compare that to your 400 CFM per ton and see if it's okay or not. All right. Duct leakage is a big one. All right, duct leakage, that is straight loss of capacity. If you have 30% duct leakage, you're losing 30% of your cooling capacity right off the top. So it's always good to do duct leakage tests. That is why duct leakage is mandatory in California if you replace any of your HVAC equipment. You have to do a duct leakage test, which really means you have to seal your ducts. You have to pass the test. I should put it that way. You have to pass the test, not just measure it. You have to pass the test, which means you have to seal your ducts to a certain point. It's that important. Okay. I mentioned the blower door test, infiltration. Infrared cameras are wonderful. They're a really good way to walk around a house and look for missing insulation, look for leakage. The problem with an infrared camera is you need a big difference between the indoor and outdoor temperatures. In order for an infrared camera to work really well, you need it to be really cold outside and warm inside, or vice versa. Okay, you need a temperature difference for them to work really well. All right. Last but not least, this is one of my favorite diagnostic tools. I have resolved issues with these little devices. They're called data loggers. There's a whole bunch of different ones, and these are quite old-fashioned compared to today's data loggers. These were little boxes. They're about the size of a box of matches, and you had to initialize them. You had to hook them up to your laptop and start them, and you could tell it how often to read temperature. You could set it for every 2 minutes, 5 minutes, 30 minutes, whatever you want it to do. All right, and you put them in the house. You let them sit for a while, and then you collect them, and you download the data back on your laptop, and then you graph it. All right. The new ones are all Bluetooth and Wi-Fi. You don't even have to, you just set them out there and you start collecting data. It's so much easier these days. You guys have it so easy. Um, but they're really, really cool devices. And you can get them to read temperature only, or if you live in Florida and you're having a lot of humidity problems, you can also get them that'll read relative humidity. All right. But out here in California, we only need them for temperature. But some of the results I've gotten from using these data loggers have been amazing. And they really, really illustrate the problem of oversizing air conditioners. Okay. So, with this information from a data logger, you can determine the equipment size relative to the load. You can determine air balance in all the different rooms. You can also determine occupant behavior. I've I I've put data loggers up, and when I got the data back, I discovered that the homeowner was not using their thermostat correctly, but they swore they did. They go, oh no, we leave it alone. We don't touch it. And I said, nope, I'm sorry. I can tell you're messing with your thermostat. I've got the data. It says right here. And there's ways to tell that. Okay. And I'll give you some examples of that. All right. I'm running out of time, so I'm going to go kind of quickly here. So this is important. Take a screenshot of this right here. If you have any plans to use data loggers, you guys will be getting these slides, by the way. But anyways, this is the important part right here. Where you place the data loggers in this house is really important. So you put one outside of the house. That's going to measure the outdoor temperature. Make sure it's not in the sun. Put it on the north side of the house. Make sure no sun shines on it. Okay, that's going to measure the outdoor temperature. Put another data logger right next to the thermostat, off to the side by 2 inches off to the side. Okay. Place a data logger right on the face of a supply register. If you have ceiling registers, you tape it right to the face of the ceiling register. Okay. And then put data loggers in the a couple comfortable rooms. Remember, I said ask the homeowner what's their favorite rooms in terms of thermal comfort, and they'll say, "Oh, oh, the library. That's the most comfortable room in the house." Put a data logger in the library. That's going to be your baseline. Okay. And then, of course, put several data loggers in all the uncomfortable rooms, the rooms that they're complaining about. Put data loggers in those rooms. Okay. If you have a house with multiple systems, do this twice. Do it for each system. You can share an outdoor temperature. Okay. You can share the outdoor temperature data logger. But if you have multiple systems, you're going to put one up next to each thermostat. You're going to have one on a register, one in the comfort room. You're going to treat it like separate houses, kind of. Okay. All right. But this is really important. This will really help you out. This is important information. Then have the homeowner agree that they're going to operate their thermostat a certain way. I did some data logger tests, and it was actually a defect litigation lawsuit, and I was an expert witness, and I was helping the builder prove that the homeowner wasn't operating the thermostats correctly, and so we actually had them sign something. It said you shall operate your thermostat in the following manner. We had the homeowner sign it. All right, and guess what? We caught them. They weren't operating it correctly. They can't leave windows and doors open and stuff like that. But let me get to the important stuff. So this red line is the outdoor temperature. Okay. These other lines are the temperatures inside a couple rooms. So you see this pink one goes up, this little brownish line goes up. All right. The green line is the thermostat, the data logger right next to the thermostat. The straight green line is what they set their thermostat to. So they wanted to set it at 76. So I put a green line right at 76. And then you can see the green line for the thermostat stays right next to that green straight line. Okay, very nice. But you look at these two things, you go, okay, that's a room that's the temperature's drifting away. That must be a problem room. Guess what? Those were comfortable rooms. Those were not rooms that the homeowner complained about. They drifted away by a few degrees, but it wasn't noticeable. All right. Here's another house. This room drifted away and it stayed away. These rooms drifted away, but they came back to temperature. And I guess this was during the day when they weren't home. So they didn't even notice these rooms getting warm. But this room got warm and it stayed warm. It never came back close to the thermostat setting. So that was a problem room. That room had too small of a duct. Okay. Now remember the register I said You put it right, you put a data logger right on the register. So when the air conditioner comes on, the temperature drops suddenly. And when the air conditioner shuts off, it goes back up. We call those icicles. All right. So every time the air conditioner cycled, it would drop down and it would make one of these icicles. So right here, it would come on, it would drop down, and then it would shut off and it would go back up. Drop down, shut off, drop down, shut off. This is fascinating to me because the homeowners claimed that this house had undersized equipment. The design temperature in this house was 98 degrees or 99 degrees. It actually hit 106 degrees. But look what's happening. The air conditioner is short cycling even when it's over the design temperature outside. This air conditioner was oversized. And you can tell that because it exceeds the outdoor design temperature, but it's still short cycling. If this equipment was properly sized, when the outdoor temperature gets this hot, this pink line should drop down and it should stay down until it cools off, and then it would drop back up. Okay, so this is a clear indication that this house had equipment that was oversized. And what happens is the rooms that aren't getting enough air because it keeps shutting off before the rooms with low airflow can satisfy, they just start drifting away. So this room just drifted away, drifted away, drifted away. This room got really hot, got up to 88 degrees, 10 degrees above the thermostat set point because the system kept shutting off. If the system would run for a long time, this room would get continuous airflow and it would go up and it would start to pull back down. Okay, so this is a really good indication of what happens when you have oversized equipment coupled with undersized ducts in the room. Okay. All right. Conclusions. I'll let you guys read that later. Basically, it's a review of what we just talked about. That's all I have. There's my email address. If you have any questions, feel free to call me, and I will let Danica wrap us up.
Yeah, thank you so much, Russ, and thank you everyone who came today. As always, if you have any Title 24 Part 6 or Part 11 questions, we offer a free code coach service to get your questions answered. Next slide, please. We will be sending out a survey in the next couple of days along with the recording and slides, and we encourage you to fill out the survey to give us a better direction on what y'all are interested in. And we have several upcoming courses that you may be interested in to supplement your knowledge, including topics such as our 2025 Energy Code Implementation Series for single-family buildings on April 9th, or Load Calculation Site Survey Essentials on April 22nd. You can sign up for these trainings and see more offered on our website, 3c-ren.org. And with that, I'm passing it back to Russ for any questions.
So thanks, everyone. Glad you got some good stuff out of it. Appreciate those comments. You guys got my email address. Feel free to email me if you have any questions. And we've got some, actually next week, I'm teaching a HVAC design class for SoCal Edison. So go onto their website and search that if you're interested in that. Thanks, Steve.
If there are no longer any questions, I'll go ahead and stop recording as well as end the course. Thank you, everyone. Thank you, Russ. Have a nice day.
Thank you.
Goodbye, everyone.